Hello, everyone, and welcome to another wonderful day of chemistry. So last time we talked about how you can use Raoult's law to determine the vapor pressure of, of gas above essentially a mixed liquid if these two systems have similar IMFs or intermolecular forces. These are called ideal mixtures. However, it turns out most mixtures aren't quite so ideal. So what really makes an ideal mixture is that enthalpy of solution is zero. So that means that two liquids mix together just like they were gases. They don't care whether they're on their own or apart, entropy dominates. However, most of the time, what we end up having is solutions where the enthalpy of reaction is going to be positive. So this means that the reaction is going to be endothermic. I have to put in energy to make two substances mix because they'd rather hang out on their own than together. Now, it turns out if you have a substance like this, it's going to be a little bit harder for them to vaporize, a little easier for them to vaporize than you'd expect. So if, say, I'm mixing together water and ethanol, and water would rather hang out on its own than ethanol, as they get more and more mixed, what we're going to have is a slightly higher vapor pressure. This ends up generating a positive azeotrope. So more or less what this means is it's going to be a little easier for that mixture to boil than either of the pure substances. So if I've got grease and water, as I add more grease, the water doesn't like hanging out there. So it says, screw you, I'm going home, and goes into the gas phase because it doesn't want to be part of a mixture. So if you have something like this positive azeotrope, the most classic being water and ethanol, what ends up happening is it's going to be slightly easier to boil a mixture of ethanol and water than it will be to boil just straight water or just straight ethanol. So we also have the other side. What happens if turns out I mix two liquids together and they like each other way more than they like themselves? At this point, we'd have an exothermic reaction. So I mix together two liquids, produces a whole bunch of energy, tells me that they don't want to leave each other. They are their best friends and will never go anywhere. At which point it generates a negative azeotrope. The vapor pressure is going to be lower than for either the pure solute or solvent. So at this point, it's going to be a lot harder to boil the substance because it doesn't want to leave. A classic example is water and HCl. As we saw, this is an exothermic reaction. HCl loves hanging out with water. Water says, you're pretty cool. You pretty much ionize, so I'm not going to let you go. And they hang out together forever. So in practice, what ends up happening is that Raoult's law only will be a good description of substances that are very similar. In the end, turns out you can use Raoult's law pretty well when you're talking about the solvent. So when your mole fraction is 100. So in this case, if we're over here, Raoult's law is going to be a pretty good depiction of X because I've got 100% X. And over here would be a pretty good depiction of Y because I've got 100% Y. If you're trying to describe the solute, you often have to go with Henry's law because Henry's law is empirically derived to talk about solute behavior, and Raoult's law is pretty good for solvents. So as a general rule, this helps avoid this non-ideal problem. And more or less what ends up happening is in the middle, you have to stitch together these two rules to make something that kind of works. But one of the other problems we have with these non-ideal mixtures is their impact on boiling points. So let's go ahead and talk about the classic example, water and ethanol. This ends up generating a positive azeotrope, which means the mixture boils a little bit easier than pure ethanol or pure water. So if I've got ethanol and water, what we end up doing is generating a azeotrope at 95 mass percent. So when I've got 95 grams of ethanol in 5 grams of water, we generate this really easy to boil system. Now this has some really important implications. So let's say I'm going to try and do distillation. So I have a system that say is about 10% ethanol and water. This is important because this is about the point at which yeast start killing themselves off because they've generated too much ethanol. So at this point, in order to get more ethanol, I have to boil it, and then I'll get some liquid, some vapor, which I condense, boil it, condense, and I keep doing that. But normally what happened is we could get a system that was 100% ethanol. Here, because of the azeotrope, it turns out you can never end up producing a vapor that's more concentrated than 95% ethanol. Because if I end up boiling the system here, the vapor composition and the liquid composition are identical. And this is one of the biggest implications of having dissimilar IMFs is you either generate a positive azeotrope, which boils easier, or a negative azeotrope, which is harder to boil. And in this case, if you're going to generate a system that generate a solution that is more than 95% ethanol, you have to do some sort of other technique. You either have to use some sort of substance that will dehydrate the solution, so it will suck up the water, or more commonly, you find a way of manufacturing ethanol that doesn't produce water. And this is one of the reasons why if you ever find alcohol that is more than 95% ethanol, never ever drink it, because it almost always has impurities because you can't get it from simple distillations. And this has a lot of implications in refining any number of other substances. And this will be a rule that we'll be finding going forward. That while ideally you can make a pure product, in practice, there's always something that gets in the way. In this case, azeotropes prevent the formation of a lot of different pure species, and contaminants are always a problem. So next time, we're going to continue our conversation with other colligative properties, specifically looking a little bit more at boiling points and melting points. Until then, take care.